Okay, we'll start. I'm very happy to introduce Dmitry Khalyavin. And he's the instrumental scientist of IC's WISH. And the WISH of IC's is very, very famous among powder diffractionists, neutron powder diffractionists, and as a very successful instrument. And most of the success should be owing to the instrumental scientist. And he's an instrumental scientist of the IC's WISH. And he became an instrumental scientist. Joined the IC's group in 2008. And before that, he graduated Institute of Solid State Physics and Semiconductor of National Academy of Science of Belarus in 2001. And after that, he did some PhD work in the Dubuna and Portugal. Is that right? Okay. Yes. And he joined, as I said, the 2008, joined ICES. And since then, he is doing work on, and his major is the magnetic crystallography, and we are very happy to welcome him, and he decided to finally come to China. We were lucky for that. Okay,
thank you so much for inviting me, and thank you so much for a nice introduction. Good afternoon, everyone. So today we will be trying to refine some magnetic structures using commensurate, using time-of-flight neutron diffraction. So the data we will be looking at were collected on the WISH beamline at ICES target station 2. But before start doing that, start playing with the data, I would like just very briefly go through basics of time-of-flight diffraction. We don't need to spend a lot of time on that because yesterday Takashi made a very good introduction to these techniques. And very briefly, I'll just go through some specific points of WISH beamline. And we will be using FullProf software to refine our data. And in order to run this program, we need two things. We need powder patterns, and we need a PCR file. So I'll just show you some key points of PCR file essential for refinement of time-of-flight diffraction data. And then we will start playing with already with the actual data. Because you had a lot of theory, so it's time to show you how it works on real things. Okay, as Takashi pointed out yesterday, if you look at the Bragg law, we can see that we can satisfy the diffraction condition by using two ways. So one of them, we just we fix our lambda, and we change angle. So that is usual diffraction way to measure diffraction patterns. That X-ray lab machine do that. And there is another way we can just fix angle, and we can change lambda. That is time-of-flight diffraction. In practice, it's easy to measure time, what takes for neutron to travel from the position where it was born, from moderator, to the position where it's detected to a detector. So it's a function of time. And time of flight is simply proportional to the lambda. So here is an example of lambda range, what we use on WISH machine. So we use lambdas from 0.4 up to 10 angstrom. And usually all time-of-flight machines are located on pulsed sources. So where this process of generation of neutrons repeated with some frequency. So at ICES, the second target station, it's a 10 Hertz. So 10 times a second, high energy protons, they hit a target. They kick out neutrons. These neutrons are slowed down by moderator and then start traveling from the moderator to sample position and sent to detectors. So you can think about that like all these neutrons from the lambda range, what we use, so from 0.4 to 10 angstroms, they're born at the same time, at the T0, during the pulse. So it's just approximation, of course, because this pulse is finite, moderator has a finite thickness and so on. But as a first approximation, you can think that they born at T0, all neutrons with all possible wavelengths in this lambda range, and they start traveling to the position, the direction of the sample, and then detectors. And of course, first hot neutrons with high energy and short wavelengths, they will reach the sample position first, and then will be scattered and registered by detectors. And then slower neutrons with larger L long wavelengths will start contributing to diffraction, and so on, so on. So like that, we will measure our diffraction pattern as a function of time. And that usually is how it looks, our Bragg, a set of Bragg peaks at certain position in time. So it will be very unpractical, of course, to use just a single detector at some scattering angle. Because time-of-flight techniques allows to populate, to cover large solid angle with detectors and improve our statistic. That's what we do on WISH. So we, on WISH, we cover our horizontal scattering plane all the way from 10 degrees up to 170 degrees, from forward scattering to back scattering. And so on WISH, detectors are simply 1 meter position-sensitive helium-3 tubes. Each tube is divided by 128 pixels, and each pixel counts its own time-of-flight data. So in total, we have 200,000 pixels, 200,000 detectors. And then we sum them together in order to get a good statistic. But the problem is that resolution depends a lot on the position of the detector, on the scattering angle. That's why we don't sum all detectors in a single histogram. Instead, what we do, we divide our detector array on 5 panels. We call them detector banks, as they're shown here with different colors. And we focus our data, we sum together the data inside these detector banks, assuming that resolution doesn't change much within these banks. Of course, it does change, but not as dramatic as between back scattering and forward scattering. And that's why when you have WISH data, and when today we will be looking at them, you will have 5 patterns. The 5 diffraction patterns are the 5 patterns which were collected at diffraction banks located at different average position of 2 theta. And these banks, actual data measured on these 5 banks, they look something like that. So this is a NACALF, it's our standard, what we use to calibrate our beamline, because some materials with unicell parameters are precisely known. So we have 5 patterns, so you can see the 2 theta average scattering angle for each of them, and on back scattering, you can see the peaks are very sharp, and then when we move towards forward scattering, then peaks becomes broader. You can actually, on this panel, you can see same peak measured at different scattering angles, at different panels, and you can see that back scattering is very sharp, and forward scattering is very broad. But at back scattering, we stop at 5 angstrom, so our accessible despacing range is only 5 angstrom, while at forward scattering, we can access 50 angstrom. So why it's like that, you can work out yourself. It all comes from the Bragg law. So we have a fixed lambda range which we cannot change. It's a characteristics of our beamline, and then based on the Breck law, you can work out what will be the accessible despacing range. Okay. And now let's talk about a PCR file. So how it will work when user comes to do some measurements on large-scale facilities like ISIS or other places. So you do your experiment, and then when it's time to refine the data, you ask instrument scientists to provide some example template of a PCR file if you're FullProf users. And we will give you an example of PCR file, how to refine knockout data. And you can use this template in order to adapt it for your own model. So all this template, so all essential parameters are set to reasonable values in this PCR file. So you don't need to do a lot. You just need to put your model there. That's what we will be doing today. And very briefly, I'll show you some essential points of the PCR file, which you need to know to approach a refinement procedure of time-of-flight data. So the first thing, what you need to decide how many patterns you want to refine. As I said, we will have 5 of them. And probably you not always need to refine all of them. You can refine all of them, or you can refine only one of them. It's fully up to you. But let's say the rule is if you don't have a peaks at very large despacing, then probably there is no point to include low resolution, low angle banks, because they probably won't contribute a lot in the information. And it's better to refine your data using high resolution banks. But very often when you have complicated magnetic structures or even crystal structure with large unit cells, you do have your peaks at a large despacing, and then you probably want to include all 5 bands and refine all of them together. So today we will be refining all 5 bands together, just an exercise in order to show you how it works. But in PCR file, this line, that is the first line, where you select the number of patterns, and if 1, it means we refine this pattern, 0 means we deselect, we don't want to refine it. But still all parameters, everything has to be specified for all 5 patterns in this PCR file. Okay, so the next stuff what you may change, today at number of phases, that probably this parameter So it just depends on the way how you want to refine your magnetic structure, for instance. Do you want to refine as a single phase using magnetic space group? That's what we'll be doing today. Or you want to refine as a separate phase, as a 2-phase, where magnetic and nuclear structures are separated. It's up to you. So job, that what tells FullProf that is time-of-flight data. That is -1 means time-of-flight neutron diffraction data. But you don't need to change it. I mean, of course, it's preset, and you just want to keep it same. Then here is a number of background points for each pattern. So usually we describe background as an interpolation between selected points. We can keep them. We can keep them like in this example. We won't change background. And later on, we will have a look on the refinement. And if we are not happy with, we can see that we need to add a few points more, or even redo our own background. But so far, we can keep this points what already there, this background, and we can start from them. And all of them will be refinable parameters, so we can change them. So again, you don't need, at least as a first step in your refinement procedure, you don't need to change them. What you need to change is the file names for your diffraction patterns. So they're here. So you just need to provide 5 files names which correspond to your data. Okay, so another parameter what I want to pay your attention is this PCR. So you see in this PCR file is set to 2. It means that after finishing refinement procedure, FullProf will generate new PCR file with extension .new, where a new parameter will be saved. So it won't overwrite this existing PCR file. So like that, we will keep our initial parameters, and we can always, if we don't like what program has done with our refinement, we can always make a step back and change something in our initial parameters and run it again. Or if it's this parameter PCR is set to 1, then program will overwrite existing PCR file. It all depends on you and how confident you are what you are doing. For instance, today we'll set it to 1 and just ask program overwrite PCR file for us. Okay, then a few here. There will be some background points and excluded regions and so on, what you can again specify later. But as I said, as a starting point, we can just keep our background like it is now. And excluded regions as well depends on the sample quality. But usually, even if we do have some impurities, it's probably good practice to figure out what impurity are and include them as additional phases instead of excluding them from the refinement at all. So in this part of PCR file, we have something specific to the beamline. So that tells the program what is average to theta for each bank. So it's again 5 lines for each pattern. And for instance, for pattern 1, our average to theta is 152, and 121 is to theta angle, scattering angle. 90 degree, 58, 27. And then we have 0, DTT1, DTT2. It's a way how to transfer data from time of flight to G-spacing. So it's how program calculate position of Bragg peak in time of flight. So it's just 0 plus DTT1 times D and DTT times D squared. So in ideal world, let's say, in ideal case, we need only one parameter, DTT1. That's the parameter. It's called diffractometer constant, which depends on the length of on geometry, on the length of our diffractometer, and ideally position of Bragg peak will be just depends on this parameter. But in reality, we always have some stuff like time signal of the target is not exactly as a data acquisition, electronics. There is some delay with how electronics reacts on Neutron registration, and so on. So that gives some global shift of your pattern, zero shift. And then DTT2 also is a parameter which depends on the nature of your sample. Is it absorbing or not? Unfortunately, time of flight data they're affected a lot by absorption, because absorption process depends on the lambda. And if a sample is very absorbing, then penetration depth will be slightly different for different lambdas, and that can affect the calculated position of the Bragg peaks. But usually it's very small, it's very small corrections. So the practical advice, how to deal with them: keep always zero shift fixed. For all, if you do multi-pattern diffraction pattern, keep zero shift fixed. And at least for one bank, and usually it's the highest resolution bank, it's also a good idea to keep DTT1 and DTT2 and don't refine them for one bank with the highest resolution, highest scattering angle. And send DTT1 and DTT2 for other pattern, you can refine them. Because like that you will take into account, let's say, that your sample is not exactly at the center of instrument, and so you always have some offset a few mils. So that is the practical advice. But if you try to refine all these parameters, technically you can, but they can correlate a lot with your unit cell parameters, and then you can have problems with your refinement. So the advice is do like that: zero shift fixed, DTT1, DTT2 for high scattering angle fixed as well, and the rest you can refine. Then you can, in this bit of PCI, you need to introduce your model. Actually, you just put your model here. So you put your space group, you put your atomic coordinates, thermal parameter, occupancies, and so on. That is your model, basically. The only what you need to remember about this parameter n atom, number of atoms. So in the current model, we have 6 atoms. In your model, probably will be something different. And if you change this bit, if you change then please change number of atoms. Otherwise, program will complain. Okay, so in this line also we control what kind of refinement we want program to do for us. So we can choose, so if JBT and I symmetry are 0, then we as in the previous lecture was explained, then we do just nuclear scattering. If it's JBT is 10 and asymmetry is IC is 2, then it's we want to model nuclear and magnetic scattering at the same time using a magnetic space group. That's what we will be doing today. So we will be swapping between these 2 options in FullProf. And finally, what else? We need a set of parameters, again, specific for each patterns. It's something like scale factor, absorption corrections, unit cell parameters. But unit cell parameters, again, is our model, and unit cell parameter, we want to keep them same for each pattern. We don't want, of course, unit cell parameters to be different at different patterns. While scale, absorption correction, and profile function parameter can be different for each pattern. So again, it's 5 times. So for each pattern, we need to specify them. And that is unit cell parameter, that is scale factor absorption. And a few words about profile function. So there are 3 of them in FullProf currently, on which we usually use number 9. So it's a convolution between pseudo-void function and pair back-to-back exponential functions. So back-to-back to describe rising part of our peak, which is usually very sharp, and then decaying part, which is described by 2 exponents, alpha and beta, and we assume that this exponent also depends on G, so they're different on different parts of the pattern, and they have this, this parameterization. And the pseudo-void function, it's a standard linear combination of Gaussian and Lorentzian components, which with same width, so same full width on half maximum. And again, it has some dependent on D, which is parameterized using sigma 1, sigma 2, sigma 3 for linear, quadratic, and so on parts as a function of D. So sigma is for Gaussian, and gamma is for Lorentzian component of the pseudo-void function. So this beats pseudo-void function and back-to-back exponential function. They describe, let's say, different contributions to profile, different physics if you want. So pseudo-void is instrumental design and microstructural effect. They go there, while back-to-back exponential stuff, it's the way how neutrons are created. The physics are related the way how neutrons are created, so how they build up in the target, and then how they moderate inside the moderator. So practically, what you don't refine this exponential parameter. So it's alpha 0, beta 0, alpha 1, beta 1. So you just, as they preset in the example, what we template. So keep them constant. Don't refine them. While other parameters like pseudo-void related to pseudo-void to Lorentzian and Gaussian component, you can refine them. So this sigma 0, sigma 1, gamma 0, gamma 1. You can have a look, I mean, when you practically start playing with the data, you just have a look at the current PCR file and see what we refined in order to get good results for our standard. And you can refine same parameters. So sometimes you don't need all three of them. For instance, for Gaussian, you don't need gamma 1, gamma 0, gamma 1, gamma 2. Very often, it's only one or two of them is sufficient. Okay, and as I said, for each pattern, because resolution depends on the scattering angle, so for each pattern, profile function parameter can be different. Scale can be different, and absorption will be different. Unit cell parameter, keep same. That is practical advice. So finally, as I said, today we will be trying to refine magnetic structure using magnetic space groups. So we will use Bilbao tools, which you already know how to use them. In particular, we will use a tool which is called max-magn, which generates maximal isotropy subgroups. And as Manuel Perismata yesterday explained, it's always a good strategy to start looking at a solution from maximum isotropy subgroups. And because they are most likely, and there is a good reason why these solutions are most likely. It comes from Landau theory, because if the part of the theory deals with a phase diagram which describes stability of different phases as a function in coordinates of phenomenological coefficients. And if you look at this diagram, they're very general, they're very general. We can find that paramagnetic phase usually have a common boundaries with magnetic phases which correspond to maximal isotropy subgroups. And usually a paramagnetic phase doesn't have common boundaries with magnetic phases which do not correspond to the maximum subgroups. And that's why thermodynamical path to something which is not maximum isotropy subgroup is very unusual, because usually this phenomenological coefficients, it's a smooth functions of temperature, pressure, composition, and so on. That's why always start from the looking for your solution from maximum isotropy subgroups. Okay, so that's why this tool is very, very useful, max-magn. You don't need to think a lot. You just generate. Usually, it's not a lot of options, and you can check all of them quite quickly. Okay, and today we will be playing with data of for this sample, for this composition, barium iron 2 oxygen 4. It has a quite complicated crystal structure and quite high magnetic ordering. You can see it's 900K. It's very high. And if time permits, we may have a look also at another data set. It's a perovskite, thallium chromium 3, which shows magnetic ordering at much lower temperatures. But this is the real data. The sample is tiny. It's a high pressure phase. Quality of the sample is not great. It has some impurities. So that something is very, very close, not to ideal case. It's very close to real data, what most of you will have. And refining of this data sometimes is a challenge. Okay, so finally, before we start playing with our data, I just want to bring your attention to something which is very important. So when you finally manage to solve your magnetic structure and you are ready to report this structure, please read this paper, this guideline, how to report magnetic structure. It's very important. You are at the very beginning of your scientific career, and it's very important you to start doing things right. And the right things to report magnetic structure is written in this guideline, how to do that in correct way. And then after, when you published your data, please upload the MC file to the database, what you can find, and again, on the Bilbao Crystallographic server, it's called MagData. Just upload your MC file there, because it's very important for other people, who are not expert, for instance, in magnetic crystallography, but who needs information from about magnetic structures, and people who does DFT calculation or so on, or who needs a magnetic structure to interpret the physical property. So they can easily download your C file and get full information about the magnetic structure from this magnetic database. So two things: the way how you report this structure, please read this guideline, and second, upload MC file when after a structure has been published. Okay? Okay, and now we can start basically playing with the data. So I hope you downloaded all files what we will be doing today. So you have FullProf installed on your machines, and you downloaded these files. So I'll be doing the refinement, and I'll be doing it very slowly. I'll explain every step what I'm doing and why I'm doing it like that. And please try to follow me. But don't worry, I mean, if you get lost, it's not a problem, because always the refinement consists of several stages. And in each folder, you can find a subfolder which is called help. So in this, if you get lost, you can go to this folder, and you can copy back a PCR where this step is completed. So you can, for instance, we will start our refinement, our data from paramagnetic data. This is very simple refinement, so it will consist only in two stages. So first step, we put model in. Second step, we let some parameters to be varied, and that's it. So if something doesn't work, you can just go to this folder, copy PCR file to the folder where you have your data, and then run it. Okay. So let's see how it works. So as I said, it's always practically, you need to start your refinement from refinement of the paramagnetic phase. And it's always assumed that paramagnetic state is null. Even when you apply for beam time, you ask beam time, you need to demonstrate the access panel, that you know the crystal structure, and you need to prove that quality of the sample. So you need to present Rietveld refinement of X-ray data collected on the sample, what you want to measure with neutrons. Because neutrons is a very expensive way to check the sample quality and so on. So it has to be done with X-ray. That's why we assume that we know paramagnetic crystal structure quite well. And then, as I said, you will start refinement of your data from changing of template, adapting the template, which you can get from instrument science, from us, or if it's some other places, you can always ask your beamline scientist to send a template file for PCR file for some standard. Okay, so let's go to folder which is called, so it's barium iron 2 oxygen 4. And let's start from high temperature data. So we have a temperature here is 1038 Kelvin, so 1038, very high. So here we have our data. And we have a C file for our crystal structure, again, which we assume that we know. And we have our template for neck half. So that's what we use to calibrate beamline. So it's a sodium, calcium, aluminum fluoride. So let's run FullProf. Let's open a Win plotter. So I'll be using, because this is Windows machine, I'll be using this one. But some Mac users or Linux, they probably will need this one. But basically it works in the same way. So first thing, let's have a look at our date first. So how we can do it? So we just do File, Open Pattern File. And here we need to specify instrument where the data were collected. So for ICs, for WISH is the ICs, we use instrument number 14. You see this one. ICs normalized data. That's what we need to open our pattern. Okay. And then we can go to place where our patterns are. You can choose directory as Ron showed. It will be looking straight away at the right directory in this case. So let's open some, we can open any, but let's start from high resolution data, from this one, 5.6. 5.6 is backscattering data. So it looks something like that. And let's open low temperature data as well to see what is magnetic, what is not. Again, same instrumental file, but it will be in another folder. It's 300K, so room temperature is already magnetically ordered. Now sample. And we open second pattern. So you can see that we have a huge magnetic peaks, which we can see even at backscattering data. So like that, we can look at other banks as well. So just, there is no need to look at all of them. So you see this two very strong magnetic peaks. This is nuclear peak. It's just a shift in unicell parameters because difference in temperature is huge. Yeah. So magnetic data 300 at room temperature, while paramagnetic data above 1000 Kelvin. Okay, so let's back to our directory where we have our high temperature data. And let's start modifying our PCR file in order to start do the refinement. So let's first rename the file, because that's what you get from us. Let's rename it and, I don't know, let's put chemical composition, let's say, in temperature at least. Because in a few months, you know, if you start looking at this data, we may not understand what we have done. But so put as much information in the title as you can. So at least chemical composition and temperature. That will simplify your life in future. So let's put barium, iron, 2 or 4, T, 10, 38 Kelvin. Okay, that is our PCR file. Then you can open that in any PCR editor, whatever you prefer. Or you can open this using editor.
Recording in progress.
Or you can open it from a WinPlotter using this, you see bottom PCR file. It will open editor. And we can, where we can modify our PCR file. Okay. So the first thing, we need to decide how many patterns we want to refine. And as I said, we want to refine all of them, I guess. So let's keep all of them. Let's select all of them, yeah. So it's 1, 1, 1. It means all of them will be. So don't need to change anything apart from we need to put the right file names here. So what is file names for our diffraction patterns? So let's have a look at our folder. So we see that we have 5 patterns with these names. So let's change. Basically, we need to change just number, file run number. So it's 42, 2, 5, 7. And we do it for each copy and paste for each of them. Paste. Okay. So when we have done that stuff, what we need to change? We need to put our model in. So we go to this place. So do you see, I mean, this file, of course, it looks quite complicated for time of flight date because it's preset for 5 patterns. So we have here background points, and we refine. We'll be refining them. We have excluded regions. We can keep them. I mean, we can start refinement from where we are now. Here, it's a reasonable start. We just need to put our model. So we can. There are several ways. The simplest way, you do it just by hand. You can simply put your model here by hand, or you can import it from CIF file using different. I don't use PCR editor. I prefer to have full control of PCR file. I prefer to modify it myself, you know, and to have as much control as possible. But still, I mean, there are some useful things, and you can, for instance, run from here this CIF to PCR file. You can take your CIF file, specified here, neutrons. It will create some PCR file for simulation, but the model will be there. So if I save this, I can give a name, let's say, CIF to PCR. CIF to PCR. .PCR. Then I have my model there, imported to PCR file. I can just copy it. To my main PCR file. So I need just this bit. And I put it instead of the current model. Paste. So as I said, now we have different number of atoms in comparison with the previous case. So we need to change here the number of atoms. You can always have a look at here. So now the number of atoms 9. Number of atoms 9. And we need to copy our unit cell parameters as well. Yes, and we need to put it for each pattern which we are going to refine. We are going to refine all of them. So let's put our unit cell parameters to all of them. So you see this A, B, C, alpha, beta, gamma. That's where we need to put them. Okay, we are done. So we can save our PCR file. And then let's have a look what we are going to refine at the very first stage. Probably so there is no gold way, universal for any diffraction and for any case, for any data which will you can follow, and get nice refinements. So it all will be different, in every situation will be different. But probably a good practical advice to always start from refinement of background and the scale factor at the very beginning, at least. That's what we are going to do. So you know how it works in FullProf. So if you want to, if this parameter at the very beginning is out, it's automatic, we are in automatic mode, then we just need to tell, if we want to tell the program that we want to refine something, we can just put one. So we have a parameter, let's say scale factor. You see, after our model, when we start already specifying parameters for each pattern, we have scale factor, and below is the code for this parameter. So if we want to fix, to keep it fixed, we put it to 0. If we want to refine it, we just put it 1. 1 means please refine this parameter. So the program will go, have a look, and will automatically assign sequential number for this parameter. So next time, when we look at this PCR file, after refinement, there will be some number with sequential number for this parameter, which FullProf decides automatically. We don't need to worry about it. So we are refining this for, in this case, 1 means we want to refine our scale factor. For each pattern, for every pattern, we refine scale factor, nothing else. All the rest is fixed. So we refine only background and scale factor. And then we will have a look and decide what is our next step. So let's run it and let's have a look. Yeah. So did I change anything? It's not. Let me have a look. Yes, it's refined. Okay, we can run FullProf by many different ways. You can run it directly from WinPlotter, from here. You see this button? Run retail program. FP. You can just press this button. It will ask you, where is my PCR file? It's here. And it starts doing the job. So it's a bit slow because it's a 5 patterns. And okay. Let's see what we get as a result of this refinement. So as I said, the model is known, so we know unit cell parameters quite precisely, and our atomic coordinates are not bad, again, because we have a good model. What was wrong to scale factor, of course, when we start, and background. That's why we started from these two things. Okay. So it's done. So it's finished because either it's converged or because it just has done number of iterations we asked. Here it's probably converged. Yes, it's converged at 10 cycles. Okay. That's how looks our backscattering bank. We can have a look at other because we're refining all 5 of them. So we can go here, PRF, and we can choose that as number of patterns. So name of the file and number of patterns. Let's choose the 2. That is another bank. Okay, it's not so bad, right? Already number 3. Okay, here we can see that the background is probably not perfect, but it's okay. It's not bad at all. That is bank 4. And that is the forward scattering. Yes. Okay. Also backgrounds. Probably this point is outside excluded region, so it's inside the excluded region, so program doesn't refine this background point. But anyway, there is no any break peaks. We can leave it like that. So far, it's fine. Not so bad. So let's do next step. So we need to decide what we are doing next. And yeah, it's pretty. So units of parameters are pretty good. So we can start refining. We can refine them again. Again, don't try to refine everything for every single pattern. You know, let's do step by step. Let's start refining, let's say, unit cell parameter, another parameter just for one bank, for high resolution bank first. Let's do it for, so we tell the program, we want to refine A, B, and C. We don't want to refine angles because we have our space group, our rhombic space group. It implies that A, B, and C can be different, while angles are fixed to 90 degrees. So let's refine A, B, and C. So we simply put ones with the appropriate codes telling the program that we want to refine this parameter. We can let vary absorption correction for this pattern again. For pattern, it's pattern 1. We are working now with pattern 1. We will keep the rest patterns fixed. Everything will be fixed. We will now, as a first step, actually second step, but still we want step by step to release parameters. Let's just release it for one pattern. And of course, we naturally it's a good idea to start the refinement from high resolution bank. So from pattern 1. Okay, unit cell parameters, absorption correction, scale. That's what we can. And we can refine profile shape as well. We can see what refined before. So it was sigma 2. Yeah, let's refine. Sigma 1. Yeah, let's refine it as well. 1 and gamma 1. You see, it was sufficient before we didn't refine gamma 2 or gamma 0 because it was sufficient to refine gamma 1. And sometimes if you let, for instance, to refine gamma 2, it will program, it can become even negative, you know, or it will be very small number. If it becomes negative, then some FullProf will complain. Then simply fix it to 0 or to some small positive finite number. Yes, and oh, sorry, I put wrong in the wrong position. Yes, I want to refine absorption. Here. Okay. And let's run it. So we just modify one, pattern 1, scale, unit cell parameters, profile function, and absorption. Again, alpha 0, beta 0, alpha 1, beta 1. This back-to-back exponential. We keep it fixed, always. It's very hard to refine. You can try to refine them, but in most cases, you will see it's very hard, and you don't need it. Most cases, there are good numbers there. Okay, so let's refine it again and see what we get. Let's wait when it's done. Okay, 6 cycles. It's converged. Okay, not bad. And then now we can do same things for rest of the banks. So we go to this bit of the PCR file after our model. And we just do same things. So let's refine for pattern 2. Now, do you see? Phase 1, pattern 2. Let's refine our profile, shape parameters. So let's copy our unit cell, because unit cell has to be same for each pattern. So we can simply copy it from here to here, because we want to keep them the same, and these numbers has to be also, so they have to be connected, they have to be tied in pattern 1 and in pattern 2 and for all patterns. So unit cell parameter, sequential numbers for refinable parameter has to be same. So we simply copy and paste for all of them, for all. No, it's quite a lot, yeah, because background points is just extrapolation between points, and for each pattern we have probably 25, between 25, I think, and 30. And let's refine for profile shape parameters as well, as I said, yeah, absorption correction. For this pattern, for pattern 3. Again, absorption parameters. They can be different, so for each pattern they can be different. Because resolution is different. Gamma 1 and absorption. And for the forward scattering, for the forward scattered banks. Okay. So we can run it. And you can, as you can see, we're already not far from, it's pretty good. Because again, our goal is today is a magnetic structure refinement, not the crystal structure, let's say. So it's already sufficiently good in order to go to the next step and start refining our magnetic structure. Okay. So we can, as a last step, let's say, if you want a further improvement, you can let atomic coordinate thermal parameters to vary as well. Yeah, actually we can do it. So we just put everything. Let's refine. Because you see, some of the coordinates has to be fixed by symmetry. For instance, this first coordinate for barium is fixed by symmetry. But I'm telling the program refine. But program is smart enough in order to understand that barium is sitting in the special Wyckoff position, and it will fix automatically this. And then I can just copy this line to whatever I want to refine, because usually this model already clearly is quite good. So I can let the program to refine everything, all coordinates. But in reality, you know, if you maybe not, your model may not be so close, and then you want to refine maybe not all atoms, not all atomic coordinates, and let's say something for at the beginning for something for oxygen or some other, and step by step to release them. But in this case, it clearly is going to work because our structural model is pretty good, and so we can refine all of them. It won't deconverge. It will work. We just copy and paste all of them. Yeah.
You have a non-centrosymmetric space group, and the origin
Oh, yeah, and we need
is
to
floating.
fix. We need to fix, yes.
Fix
That's
one
right.
coordinate of the
Yeah,
one
we
Z
need at least
coordinate.
one coordinate. It's correct, absolutely correct. Right. So do you see, look at our space group. Yes, because it can, so our space group is non-centrosymmetric. So C-axis is a twofold axis, so we can have a global shift and we can have a global instability in our refinement if we let to refine all Z coordinates. So we need to fix something. And programming in this case is not smart enough in order to, do you see, Ryan? I trust too much your program. So we need to fix something. Let's fix iron. Z coordinates we don't want to refine. Okay, and that's it basically. We can run the final refinement and go to the next step, to our magnetic space group, to a magnetic refinement. Okay, we can check other banks as well to make sure that they don't look bad before we go to the next step. So let's have a look. So it's PRF. That is our, yeah, doesn't look bad. Bank 3. Okay, not bad. It's a background, but it's sufficiently good. We don't need to, I mean, you can refine when you do your refinement and when you prepare already for publication, yes, you probably want to add some background points here and do some better job, but for so far we are not bad. And we just check all of them to make sure that, yes, it's okay. It's sufficiently good, definitely sufficiently good in order to go to the next stage. Okay, now we have our model, we have our PCR file. We refined our paramagnetic phase. So let's copy this PCR file, this one. Let's copy it to the folder where we have low temperature data with name 300 Kelvin. Just Control C. Go to here, Control V. Okay. And let's change, again, let's start from changing the title. Just to make sure that next time we will start looking at this data, we understand what they are and what's the refinement. Yes, G300K. No, you can, but it's not. Yeah, you can have a space, and anyways, there is underscore here. It's just on the screen. It's not shown. Yeah, but I think you can, right, Ryan? It won't complain space. It doesn't like. I know it doesn't like, but. Which may not like it. Yeah. Okay. Yeah, so it's better don't put spaces in the name of the file. Don't put spaces. Okay. And then let's open. Let's go to the 300K where our data are. Let's open our PCR file, and let's modify it again. So let's put our right file names, because now it's our low temperature data. It's something else. It's 42193. 193. Let's copy it. and send. So actually, you can see that our paramagnetic data were collected at 1000 Kelvin, while magnetic data is room temperature. So it's a huge difference. And we are using structural model from paramagnetic data, which is really far from. So our model is not as good as before. So let's see first, as a very first step, let's see where we are. So we don't want to refine anything so far. Just let's see how this model works for low temperature data. So let's fix everything. So we changed our file names here. Let's put this parameter out to 0. Okay, this parameter. So it was 1. We put it to 0. And let's put the number of refinable parameters 0 as well. We don't refine anything. We just want to see where we are now. Because, as I said, there is no way, which can work for all situations. So our next step will depend where we are. So we need to see where we are. So let's just run it like that. And just see what is the best to do next. So we just run again. So we just to go to WinPlotter, FullProf, run, and see. So it will do just one iteration and stop. Okay. Do you see now it's generated new PCR file? Because before it was saving to PCR, but now it's complaining and said that because we have magnetic peaks and our model is really far from a good one, our chi-square is much higher. So it created new file. If you look now in this directory, do you see PCR? That it's created new file with extension new. We can keep it, or we can, so if you want to avoid that, what you need to do, you just need, before running that, you just put, instead of 40 chi-square, put a lot of zeros, let's say, like that. And if you run it now, then it won't complain, it will just rewrite this. But doesn't matter for us, we're just looking for where we are, and definitely, as we suspected, we are far from, right, because our model was somewhere at very high temperature collected. And apart from the magnetic peaks, yes, which we do know what the magnetic model is, the obvious, the very first obvious is our unit cell parameters are wrong. Yes, it's quite natural. And again, I mean, this is room temperature data, and it's very likely that we have X-ray diffraction data collected at room temperature. So where we can take, from where we can take our unit cell parameter. So let's assume that we do have this room temperature data. Yeah, so let's open our PCR. And in this folder, you can find, in this T, at the very end, you can find unit cell parameters at 300 Kelvin. Just open this folder and copy unit cell parameters from here, assuming that's what we are getting from room temperature X-ray data. We copy and paste it to our PCR file. Again, 5 times, because we are refining all of them. ABC parameters for each pattern. And now let's again have a look to make sure that, yeah, our unit cell parameters are indeed sufficiently good to start. We can ignore that, or we can even delete that. Okay, much better. Indeed. So we still, yes, this of course our magnetic peaks, but at least our unit cell parameters are not as bad as before. So it is sufficiently good now our refinement in order to do the next step. The next step is we need to find the propagation vector. That is a very important step to get our model for magnetic structure. So what is the practical advice? So as Ryan said, that there is a tool which is called K-search, which you can use. But I would advise at least start just from the checking all special points in the Brilliant zone. Just check them by hand. So you can go to Bilbao server, where there is a tool so in the group of program, it's called space group symmetry. There is a program which is called KVEC, where we just need to choose our space group for paramagnetic space group, for paramagnetic structure. It's a number 36, this one. And generate list of all symmetry distinct points of the Brilliant zone, so our propagation vector. And then what we were interested in, we're interested in the propagation vector, where all three components are fixed by symmetry. For instance, 0, 0, 0, 0, 0, half, 1, 0, 0, 1, oh, that is our point of symmetry. You see, here we have also lines of symmetry where one of the parameters are not fixed by the symmetry. So that means that if component of the propagation vector changes this component, symmetry of the propagation vector stays same. So it can be any. So that is the case of incommensurate structures. But as a very first step, and probably in most cases, you will have commensurate phases. So we just need to check our special points. So ignore all lines of symmetry, planes of symmetry, where two components are not fixed by the symmetry, or general point where all three components of the propagation vector can be different. And we need to check only special points. Okay, so we can use this tool, Bilbao tool, or you can also, IsoDistort provides this information. It's a choice, but this is very easy. This Bilbao tool is very easy to use. You just generate this list and you go one by one. So how practically we can do? So then we need to index. So what we need? We need to find a model. We need to find a propagation vector which will index, which will put our Bragg peak position in the right place on the pattern. So how we can do it? The simplest way, let's modify our PCR file. So let's temporarily introduce another phase. So we go to the very top of our PCR file and choose number of phases 2. We want 2 phases. And then copy our existing phase. So we have one, which is started here, data for phase number 1. You see? So you have number of refinement parameters. Then you have 5 lines describing instrumental parameters. And then our model starts. So we want all that stuff all the way until absorption correction, including absorption correction for the last pattern. Copy. You see that bit? That's what you need to copy. And paste. And then we don't need this atomic coordinates and whatever for this. We just need for indexation purpose, we can delete all atoms. We don't need them. And we don't need space group with extinction, because you see this space group has extinction because it has a glide plane and has a screw axis. We don't want that. We don't want any extinction apart from the center. That is our space group. So we deleted atoms, so we need to delete, we need to change number of atoms to 0. Okay? No atoms. Number of atoms to 0. And now we can put our propagation vector. It will be special point. So k minus k equivalent. Positive number, 1. And then we can specify at the end, at the very end of our PCR file, we can specify our propagation vector. 3 components of the propagation vector, 3 flags, because it can be, in general case, we can vary component of the propagation vector. Okay? Safe. So far our propagation vector is 0. That is special, it's called gamma point. It's listed in our Bilbao tool as the very first special point. So let's check it. Be safe. Again, we don't refine anything. We just want to see positions of our peaks, predicted peaks. That's only what we need. Save and run. And one by one, we will be checking all until we find which of them will work, or if nothing works, then we probably want to use case search. Okay? Yeah, it didn't work. We couldn't index. So let's move to another point. 0, 0, half. So we go to the end of our PCR file. And now do you see, so it's rewritten there. This bit, it has done it in a proper way, and we put propagation vector 0, 0, half. We save and run it. So I'm doing it slowly, in order to make sure that you follow. But in reality, it's very quick. You will check these points very quickly, like in 5 minutes. Everything will be checked. When you know how it works and what you are doing. Yeah, it's quite slow because it generates a lot of reflection. Look at this bit of the pattern, how dense it's a many of reflections. So, again, didn't work. We missed. So we go again to our Bilbao tool 100. So as explained yesterday, Manuel explained at this point very carefully that for centered unit cell, K0 is not equivalent to, for instance, 100. Because 100 is not a proper reciprocal translation. So the proper reciprocal translation for C-centered cell is something what satisfies H plus K equals even condition. That is a condition for C-centered cell. That is a condition for the allowed reciprocal translation. 100 is not. Therefore, 000 and 100 are different propagation vectors. So it's very easy to understand what is the difference. For instance, because if you have C-centered cell and we have a magnetic atom at the origin with coordinate 0, 0. Then we will have also, when we apply the cis-center translation, we will have an atom at the position half, half 0. So in the case of K0 magnetic structure, moment on the 0, 0 and half, half 0 will be parallel to each other. While if propagation vector is 1, 0, 0, it's something what violates this cis-center translation. Then these two atoms, magnetic moment on these two atoms, will be anti-parallel to each other. That's why it's they're not equivalent. Okay, so let's put our 1, 0, 0. Let's check this propagation vector. So we put 1, 0, 0. We put C component vector 0. And run it. Okay, it's done. It's just writing, saving the date. And now, yes, we can index our peaks, our position, our predicted peaks at the right position. Okay, now we know the propagation vector. And we don't need basically go and explore further. But you can do it. You can do it yourself and verify that indeed this propagation vector is the only one which index our pattern. Okay. So now when we know the propagation vector, basically, now we don't need anymore the second phase, so we can open our PCR file. We can simply put here number of phases 1, and that's it. And run it, let's say, and program will get rid of the second phase automatically. Okay, the only what we need now, we need C file. And our propagation vector. And then we can, as a next step, we can, as Manuel explained it yesterday, we can use our another Bilbao tool, which is called MaxMagn. So we generate maximal magnetic isotropy subgroups. Because as we discussed, that is the most likely solution our solution will be one of them. Okay, so in our folder, we have, I guess we should have some C files generated automatically. So it's, for instance, this one. No, let's yes, for instance, this one is PCR file. So it works like that in FullProf. If this parameter RPA is -1, then it will generate PCR file. If it's 0, it won't. But usually, I mean, it's preset as -1. So let's go. So let's go to Bilbao tool, and let's try to generate our possible magnetic space group, maximal magnetic space groups. So we just need now another block of the program, this magnetic symmetry and application. We go there. We find our MaxMagn, it's this one. We tell the program that we want to use C file. And we specify our propagation rate. 1, 0, 0. We do submit. choose the file. That is our C file. We do upload. We tell the program that we want magnetic iron 1 and iron 2. That's what we want to see. That is our Wyckoff position of magnetic atoms. And do submit. Okay. The program generated, you see 4 candidates. So we need to decide which of them we want. Sometimes, and it's quite often the case, so we can use this MAC-Ext, do you see? So if we click that, it will give us conditions, reflection conditions, for magnetic reflection condition for this magnetic space group. But in this case, they all will be same for all 4 of them, because we just centering this, just that one bit of all the rest is same. So that won't help us a lot. Okay, but it's still only 4 choices. It's not so big number, and we can check all of them one by one. But I won't waste time, checking all of them. I just tell you that as far as I remember, and not 100%, but I think it's this one. It's this number 3. So this space group, I hope will do the job. Yes. Okay, so we can go to show, and then the program will tell us go to setting standard. So in order to do standard setting for this magnetic space group, you need to swap A and B. Do you see? Yes, we want standard settings. So always try to follow and do things in standard settings. That is the advice. I mean, I know that many people prefer to keep settings of paramagnetic space group, but I think in many cases it's not justified anyway. So it's always better to use standard setting, in my opinion. So let's use standard setting for this space group. So we go to the standard settings, which requires changing of unit cell parameters. And origin as well, yes, yes. And origin 1/4, 1/4, 0, yes. And then we do export data to MC file, because we want MC file. That's what we need in order to do the refinement. And we download our C file. And let's copy it to the folder where our refinement is. Okay? So far it's clear, right? It's quite easy. So we have also tools. So now we need to implement our magnetic space group into our PCR file. So we need to import. So you can do it either FullProf tools, or there is a tool at the Bilbao Crystallographic server that's mshift to PCR. This one. It will do exactly the same job. You choose the file. is our MC file. I can go to downloads. We do convert, we download it. So that is our file now downloaded, which contains, this file already contains our model. We can open it with any editor. It contains this bit, that's what we need. Just open our PCR. We paste, we replace our nuclear structure. With a magnetic space group. And now we need to change, so we need to tell FullProf that we are going to refine both crystal and magnetic structure. And we are going to use the option in FullProf magnetic space groups. So this is controlled here. JBT has to be 10. IC has to be 2. That's what we need to change to tell the program that, okay, save. And of course, we need to copy and paste our unit cell parameters again, because you remember our standard settings require swapping A and B. And, but we can go in our mshift to PCR file, where we have the right unit cell parameters. They already swapped. We can simply copy them and paste back to our PCR file. Okay. So I suggest to make a break, maybe 5 minutes. And then, because we still have something like 50 minutes, right? Or go. Okay, so let's make a 5 minutes break and at 7:40, no, sorry, 7:40 is UK time.
So 5 minutes break.
Yeah, at 15:40. That you that you follow. So guys, if you are lost, as I said, let me show you again. So in each folder you can find subfolder help, that in order to run PCR file, so you cannot run directly from help because there are no experimental patterns, there are no diffraction pattern in this folder. So you need to copy. So you need to take whatever you want, let's say we are in what we completed now, let's say indexation step, right? So you need to copy this PCR file, copy to this one, which contain our patterns. So if I put now do paste, and run this file, PCR file, now it will work, because it's looking for our data, experimental pattern. Because many of you asked this question, so it doesn't work. The PCR file in help doesn't work. Yes, it doesn't work, because it doesn't have patterns there, our experimental data. So you copy from help, copy to the main folder, and then run it if you are lost. Okay? Okay, so let's back to our business. So what is, we finished where? So we are working with this one. So we put our magnetic space group, right, into PCR. So we have done MSIF to PCR. That's what we have done. And we implemented model. We placed unit cell parameters, which are transformed. So it's also very important to put the right unit cell parameters, which are transformed, which are correct for the transformed cell. Because if you leave them like they were before for paramagnetic space group, then obviously your diffraction pattern will be completely different. It will be a mess. It has to be unit cell parameter, has to be transformed as well to the standard settings of this magnetic space group. Okay, so let's make sure that we haven't done any mistakes. So again, let's just run it and see that the program doesn't complain, and it just do the job. Okay, so if you are lost, copy and paste from help, copy and paste the appropriate PCR file to the working directory. Okay, let's run. So far we are not refining anything, if you remember. So we just were doing indexation first, and we generated our magnetic space groups, and then we assume again, I'm not 100% sure that we are taking the right magnetic space group, but we will see. If it's wrong, then we may need to take another one. Okay, so it works. So it worked, but everything is fixed now because this parameter is 0, this one, a number of refinable parameters are 0 as well. So let's start refinement. I mean, let's see what we get. So let's undo this. Let's put it to 1 instead of automatic. That's it. We don't need to set, because it will automatically take all refinable which we want to refine, which with keywords non-zero. It will take all of them. And so we don't need to put here anything. We can keep it 0. It's okay. We just change that one number, automatic from 1 to 0, from 0 to 1. Okay, and let's give a start. No, what? Sorry, what is? It's I'm using the wrong PCR, because that one which I showed you what you need to copy. So let's just delete it. So we need this one. Yeah, this one. So let's do again 1. And let's give some start, because usually program doesn't like when we start refining parameters from 0. So we need to give some finite values to them. So let's give the first 3 numbers. So you see now it's organized in slightly different ways. So we have iron, which is magnetic in our magnetic space group. And we have our atomic coordinates, x, y, z, thermal parameter, which is set to 0 because of this MSIF to PCR and so on. We will refine them later. And then in the next line is the first 3 numbers. That is our component of the magnetic mole. MX, MY, MZ. So we need just, instead of 0, let's do some, I don't know, 1. Let's say, and for the second atom as well. I mean, again, we are just trying, some starting combination, let's say. I don't know is it good or not. Our data are good, pretty good, and of course it will depend. So as a first try, let's say, we can do all of them. Let's say we have 2 iron, non-equivalent, symmetry non-equivalent, and we are allowed to change all 3 components of the magnetic moment on them. So let's try first of them. Let's say as a first step, let's vary all of them and see what happens. If it crashes, then we will we will fix something, and we will use less parameters. And again, yeah, I don't know which of them are good, which of them are not. What is a good start? What is a bad start? But 6 parameters is not so. It's not a lot. We have a lot of magnetic peaks and data, very good quality. So we can 1, 1 minus 1. I don't know, 1 minus 1. Because if it doesn't work, let's say like that, we can change our start, let's say, and we can change, let's say, we can do 1 minus 1 for X component, or we can keep, let's say, and we can fix Y and Z component and vary only X component as a first step. Then if it doesn't work, we can check B component and C component and so on. So, I mean, nobody tells you, which start will be good in order to find the solution. So it's every time it will be different. But this is not a super complicated case, so I think we should not struggle too much to find our solution. Okay? And then let's try, let's see what will happen. Just refine and see. Okay, so you have done this step, right? So essentially this one. This one. So we need to back to the mode where we can refine our data. And we need to give some start for our magnetic moment for iron. That's what we have done, these 3 numbers, here and here. Okay, let's run it. No, sorry. Another point, of course it's not going, because we forgot, we forgot to tell the program that we want to vary them, right? We just put them to some values without, and we forgot to tell that we want to vary them. Yes, do you see the flag below? They need to tell FullProf, yes, we want to vary them. So let's vary them without any constraints. Later on we may put some constraint. But so far 6 parameters. File, save. Okay? Because you may run it like that, and it probably won't change anything. It won't do a lot, because it was not allowed to change magnetic moment. So I'll just give you a minute in order to finish your refinement and then change it again. Then open your PCR file, then go again to your model, where your model of the magnetic space group, and tell the program that you want to refine component of the magnetic moment for iron 1 and for iron 2. Okay? And let's run it again. Okay, it's doing something. Looks promising. Yeah, okay. You see, it's found solution. 6 parameters was okay. We don't need to restrict our refinement. But usually, I mean, it's not very often, you know, and usually maybe it's not a good idea to start to refine all parameters at the beginning. So you probably, as I said, you can just vary some of them. Let's say on the X component or Y component, and try Y by one. Okay, so it's good. So let's have a look what when it's finished, what we have. Okay, it hasn't converged yet, but it's not bad at all. So let's have a look what we are getting. So what our moments are. So we can see, right, that it wants a B component of the moment to be big and to be anti-parallel on two atoms, while component on the X and Z, they're very small. So what we can refine now, so we can start refining structural parameters as well, because so far we keep them like they were refined for 1000 Kelvin, even above that. So they're probably not good. And particularly what is definitely wrong are thermal parameters here, because they're just set to 0. When we were converting MSIF to PCR, it's set to 0. So let's give for thermal parameters some finite values like 0.5. They're reasonable. So be careful with iron, because the first line is atomic coordinates and thermal parameter, but the second line, don't touch it, because so the first three parameters, the first three is magnetic moment, and the other three, they're meaningless for this way how we are refining magnetic structure. So just keep them to 0. And then for this iron, for iron 2, again, thermal parameter 5. You see, so it goes thermal parameter 0.5, 0.5, 0.5, 0 for iron, second line, then again 0.5 for iron 2, then again 0, because it's not what we want to refine, and then again for oxygen we can put something 0.5. .5, 0.5. And then we just tell that we want to refine them. So at the keyword below, we just tell, if you set it to 1, that we want to refine this parameter. If it's 0, it is fixed. But we can refine all of them. Okay. And what we can do, we can constrain our iron 1 and iron 2 to have the same size of the moment for B component. We can set probably this to 0, or if you want, we can try to refine like that first. Let's say, let's do it as a final step. Let's say, let's decide later when we have a bit better fit. Do we want to keep refining X and Z component of the moment, or are they statistically significant or not? So let's first, because the main now problem is a thermal parameter. We need to refine them. Okay, and let's run it. Because you see sometimes space group allows you to have a component, all three components of the magnetic moment to be non-zero. But your data, so if symmetry, that means that magnetic symmetry allows them to be. If magnetic symmetry allows, or any symmetry allows, it means that these parameters will definitely be non-zero. They can be very small, but they will never be zero. Because this is not physical, it's a general rule. So some physical quantity can be vanished, can be exactly zero, only if it's a requirement of the symmetry. If symmetry doesn't require this physical quantity to be zero, it can vanish accidentally at one point of phase diagram, but then it still will be finite. So if space group, magnetic space group, allows all three components to be non-zero, the all three components will be non-zero. But your data may not be sensitive enough in order to refine all three components of your magnetic moment. That is the point. And that's what we need to figure out. When we do the final refinement, we will have a look at the size of this component and their standard deviation. Okay, still not converging. So do you see it's fluctuating? Our refinement doesn't want to converge because probably our data are not sensitive enough in order to refine all components of the magnetic moment. So let's constrain. First of all, B component for the iron 1 and iron 2. So let's set them to, let's say, 4 maybe to this value. Let's copy this value from the iron 1 to iron 2. And let's change the number, sequential number for these parameters. They have to be same with opposite sign. 1561 minus. So now we constrain B component of iron 1 to be anti-parallel with the B component of iron 2. Okay, we can try now to run again. Well, we can fix, definitely these are, I don't know what create. Let's run it like that first. Let's see what will happen. So I started constrain this component because it's obviously the main. So that is our primary order parameter, this antiferromagnetic component along the x-axis, because that has a very large value. So refinement is very sensitive to this component. But still, it doesn't converge, so it fluctuates because it still doesn't like something in the refinement. So let's see how constrained refinement. behalves. Because if everything is fine, if everything works fine, it has to converge. We have to reach convergence. If for whatever reason it doesn't converge, it means that we have some correlations, you know. Yeah. Yes, and yes. We can have a look, because when refinement is done, it generates several output files, including MC file, which will contain the standard deviation. So you see, so it tells that it's not happy with RZ component. It's a moment along the Z-axis. So probably our refinement is not sensitive. We are trying to refine something. What our data doesn't contain, let's say, information about that. So we can have a look as Ron, but even from that, it's obviously that we just need to fix it. You are not sensitive to that. It doesn't want to converge because as that component is probably fluctuate like crazy. And what we can do, yes, we can go to this directory where we do the refinement. We can have a look at the output data. So there is a, you see this file with .sum that will contain information, or MC file. So it has to generate for us MC file, this one, which also contain information about magnetic space group. So let's open this file with and see what so no, it doesn't look right to me, no? Is it correct? Yes. Let me see. No, it is correct. Yeah, so it's correct. So that is, yeah. Sorry, we can let's have a look again. On this MC file, and yeah, let's have a look at the standard deviation. Do you see, for X component, the value and standard deviation, so standard deviation is not just 3 sigma, it's bigger than the value itself. For X component and the Y component. So that means that we will never refine reliably this component of the magnetic moment, because simply they're too small for powder data. So again, I want to stress that they definitely not zero, because there always will be coupling. Symmetry will impose coupling. But our data are not sensitive to this component, and we just need to fix these parameters in our refinement in order to converge. So let's just fix them. We can fix them to zero, because since our refinement is not sensitive, we cannot claim any value. We cannot claim this value, you know, in the paper, because they're meaningless for R. Let's just fix it to zero. And same for that component. Okay. Just zero. Okay, just let's see, make sure that it converges now. So what is the advantage to refine the data using magnetic space group? Because we can refine our structural degree of freedom, which are allowed to be, so we can refine our magnetoelastic coupling, basically. Because if we do refinement as a two magnetic, so as a magnetic phase separate from the nuclear one, and we keep it symmetry of the paramagnetic space group, we may not have, you see it's converged to the first cycle, just because we fixed the parameter which was fluctuating. And doing the refinement in magnetic space group, we can refine our magnetoelastic coupling, which sometimes it's assumed that it's small. But it's not always. I mean, if you have a good quality data, you can see significantly, statistically significant magnetoelastic coupling. And the right way, let's say, strictly speaking, the right way is to refine this effect, especially in magnetically frustrated system. Magnetoelastic can be very, very big. Okay, so we refine it, so we converged. So let's have a look and do final adjustments. So what we can refine, we can refine our atomic coordinates. So we are refining our thermal parameter. We can now to refine our atomic coordinates. Again, remember that we need to fix, because it's still non-center symmetric, right? And it's still C-axis is the polar one, so we need to fix. We need to keep at least for some of them, yeah? No, I did it at the very end. At the beginning, they were free. I can make them free. Yes, you want to refine separately. Yeah, okay. Because they symmetry unrelated. In theory, they can be different. But again, we can have the same problem that our data are not sensitive enough in order to sensitive. Yeah, let's make them different. Because I was fixing them just to eliminate some correlations, and avoid to converge the refine. But we can make them different. Yes, and let's refine structural parameters as well, right? So let's fix again. Let's keep fixed for iron. Let's keep that component of the atomic coordinates. Yeah, that is what by default I think. Yes, it won't change a lot. Let's put it 3. Yes, it's probably default form factor at the Bilbao, because MC was generated by it was M2. But yeah, we can put it. The right value will be 3+. That's correct. Okay, so and for oxygen, let's make oxygen also free. Let's make the refinement unconstrained. All of them. So we can decide, in PCR file doing like that, so we can full control what we want to refine, what we don't want to refine. So it's fully up to us. So let's refine oxygen as well. So unit cell parameters, I guess we're refining. All the rest should be fine. All the rest, absorption correction, everything is free. So we just now we are refining magnetic moments on iron 1 and iron 2 independently. Sorry, say again. Nothing, it will fix to 0. Yeah, we can do it. Program is smart enough. It will fix it. It will. No, you see, for instance, 0.25. This component is fixed by a special Wyckoff position. So let's tell the program we want to refine, and let's see what it will do. I think it will fix it. Okay, it's converged, so it didn't complain, you see, so no problems to refine X component, Y component for magnetic moment separately. So let's see how different they are. Okay, so that is something we can have a look at other banks. Okay, they're not bad, right? So let's see the final result of our magnetic moment. Okay, they're slightly different, yes. Let's see how is it different statistically significant. Again, let's have a look at the MC file. So 16, yes, it's probably, no, 2 sigma, yes, probably not. So it's, as a final refinement, you see, it's still the difference is 0. Roughly 4. We can keep, yes, we can keep them final refinement like that. We can keep them independent. In principle, yes. I mean, it's a symmetry unrelated positions, and there is no any reasons. There is no symmetry reason why the magnetic moment size on iron 1 and iron 2 has to be same. So we can refine, and refinement converges. So it's not fluctuating or whatever. So we can take this result as a fine. Okay, so it's something like that. So you can do some better job with probably with the background and so on, because we did the refinement using background from, but it's not bad. So that's how it works, basically. That's how it works, and that's how you can solve. So when you know this with all these steps, basically you will do this very quickly. You will generate your magnetic MC file. You can check all of them, one by one, and it will take not a lot of time for you. So it's a very convenient way to refine, and it's very convenient tools, were developed, and so just use them. Okay, so basically we are almost time is almost time. So you can ask your questions now if you want.
One thing, you can represent also the contribution of the magnetic phase, or the magnetic component. I think that there is a file that you can open with WinPlotar also, which you have only the magnetic component with another color just to see how big is the magnetic.
So you mean make a subtraction?
No, not subtraction. Just open a file with this. I don't know if with this WinPlotar is possible, but just open the file, maintaining the PCR file.
So you mean
Yes,
this open
pattern file,
yeah.
yes. Let us see. Yes, I suppose that is.
No, I've never seen.
It's just the first one. Instrument number 10. Yes.
This one?
Yes, open. No, it has not been. Yeah, well, you have a yes. Go down. No, this is not the no summary.
No,
there is no sub. No sub. Well, I don't remember. But you can look the component, the magnetic component, purely magnetic component.
Right.
But you need to turn that on first.
No, I mean, I usually do subtraction in order to do that.
No subtraction. There is a
model.
calculation.
You mean model?
The model, this is just to see how big are the peaks. Because, for example, here in time of flight, you are going very far in Q, and the contribution is negligible.
Yes, for factor
then
will
you
do the job.
You can control that
Yes.
in order to accelerate the calculation, because you are putting plenty of reflection that are zero.
Or we can, I can have a look at this option, and then when Francois will be giving tomorrow tutorial, with another FullProf tutorial, we will show you this option. Okay. Any questions? Yeah.
I have a question. To what degree you think the refinement is good? Because I found the chi-square is too high, maybe, especially for
Yes.
pattern 1. It's up to 100. So
It's all nominally, it depends on the statistic of your data. If your data statistic is good, you will never get chi-square small. So it all depends on chi-square is a good parameter in order to compare different models on the same data sets. But it's not good parameter, let's say, in order to compare refinement which has been done on different data sets, because this parameter will be strongly dependent on the statistic of your data. So if you want to compare parameters of models which were refined on different data sets, the only meaningful parameter is ABREC, is this one. This one. And they're pretty good. 3% is pretty good break. So just don't pay attention that chi-square is very big. So it doesn't matter. Just compare. So if you do refinement in another space group, using same data set, then yes, pay attention on the chi-square. Which model has a lower chi-square probably has more chances to be correct one. But don't worry that chi-square is high. It simply tells you that your statistic is very good. On WISH, it's always, you will never get chi-square 1, never.
So in that case, the refinement is good?
Yeah.
Is the refinement is good enough? Even the chi-square is up to 50.
Yeah. It's
Okay,
still good.
thank you.
It's still good. It can be 100 or it can be even several hundred. There is no good or bad number. What you can definitely take. It's good or bad number when you're comparing different models. Yes, that will be a good number. But if you compare different data sets and look at the BREC, integrated intensity, that is what you can compare with refinement what you have done on your data, and someone else have done a refinement on their data and reported ABREC. Since this is the only meaningful factor what you can compare, cross-compare, and decide which refinement is better. All other depends on the particular quality of the data. And you cannot, if models were tested on different data sets, on different patterns. And there is no point to compare a factor. Okay?
Thank you very much. I noticed that in your lecture, we add a magnetic structure just in one phase. I mean, before this, when I performing the magnetic structure refinement, I already add a second phase as a PCR file. Yeah, and so what should I do if I want to add another magnetic structure phase? I mean, maybe I'm facing some problem that only use one. I cannot reproduce the experimental data. Only use one magnetic structure phase, and I want to maybe do refinement with using two magnetic structure phases together. So what should I do if you think this?
So you need to know the magnetic space group of another phase.
Yeah, yeah.
And add another phase, just like we did in order to index our pattern. So you just go here. So you change this parameter to 2, and you introduce another magnetic phase like we did in same way, and refine two So if your data contain information about phase fractions and it have a magnetic peaks, let's say, from different magnetic phases, you should be able to refine that, yes, in two-phase model. Should be all right, yeah. In same way as you do refinement of the normal nuclear structure, crystal structure, using two-phase model. Yeah, it should work in pretty similar way.
Okay, thank you very much.
Thank you. My question is following the previous one. Because I tried with two magnetic space group using Bilbo surface, I mean 2K vector. So I get two magnetic phase, right? Just like the one you used. If I put both of them in one PCR file, I think I will have like two nuclear phase at the same time. Because
so it depends how did you try to do that. Because you're probably talking in the way when you refine your magnetic structure as a separate phase.
Yes.
And yes, you will have this problem. So because you will have one nuclear and two magnetic, how to scale that?
Yeah,
yes,
exactly.
that's probably what you want to say is the problem. But here we are using, basically we are using, yes, two magnetic phases. Two magnetic phases. And in theory, if your data contain information, about these two phases, if you have a, let's say, isolated peak, which belong to one phase, and isolated peak, which belong to other, you should be able to refine this data. If it's not the case, then probably, yes, you will struggle to refine your data using two-phase model. But if, as you said, that in your case, your magnetic model had different propagation vectors even.
Yes.
So they cannot, let's say, scatter in same position. You probably will have magnetic peaks from one magnetic phase and from another phase, which don't interfere, don't overlap. And in theory, you should be able, but the only question is, why did you decide that it's a two different phase, but not one phase with two propagation vectors?
Oh, okay. yeah, I understand.
Yeah, so depends on the situation. I cannot tell you, maybe you are right, maybe it is the case of two phases, but again, you can easily have a situation when you have two propagation vectors in the same phase.
Okay, thank you.
But if it is a two-phase, you should be using this two magnetic space group. In theory, you should be able to refine your data. Yeah. No, yes, your magnetic moment will be scaled to. So it depends again. So if you can, because why you have two magnetic phases? Because if it's only one nuclear, it's very unlikely you have two magnetic phases. So there must be probably two nuclears as well, right? And so if your data, if this nuclear scattering from this magnetic phase do not overlap, so you should be able to refine your data. Because scale factor for each of them will be independent, and you should be able to refine them independently, and scale your moment size and scale your phase fraction in this case. Yes, for each phases you will have your scale factor. Yes. The problem is if they overlap, and you cannot refine, then because in this case phase fraction and moment size can 100% correlation. Again, it all depends on the data and situation. Because if it is the case, if you cannot separate nuclear scattering from different phases, and you are trying to refine two magnetic phases and only one nuclear, then of course you need some additional constraints. Either moment size, so you need to, let's say, constraint put that your moment size in two phases is same. Then it will eliminate instability, and then you should be able. Or otherwise it will be 100% correlation between phase fraction and the moment size. Yeah?
Yeah, so normally there's 5 banks. I think in your case you refine them at the same time, but if there's absorption, for example, European, maybe we shouldn't do that. We should focus one bank first.
Yes. I mean, it's all arbitrary. You need to decide what is the best situation. I did it just because you can, in theory. You can refine all of them, and I just wanted to show that yes, you can refine all of them. Example for. But of course, I mean, you need to decide, because even in this case, we probably didn't need bank 110 because our model doesn't have and our data don't have any bragg peaks at very large spacing. Yeah. And of course, for like in your case, for European samples, you have a very strong absorption. And it will complicate a lot because this absorption will be it's strongly lambda dependent on wavelengths. And yes, I would recommend doing refinement of this strongly absorbing samples using only one bank. So, one of them, let's say, choose which contain all peaks. What you have. Let's say bank 29 for magnetism. In your case, I think it was bank 29, which contain all magnetic peaks. And then using in the refinement of magnetic structure just only this peak. You will have more chances, let's say, to model absorption correctly and get a meaningful size of your European moment.
Yeah, so maybe a more general question, what's the strategy for the absorption strong sample for the multi-plan banks refinement? A general strategy?
No, I mean, generally what you can do, I mean, it's very hard to refine them, and very often, yes, you have unphysically big or small moment, Sometimes what I do, let's say, when I refine, I simply fix the moment of European to 7 maybe, and then refine absorption. That is one of the way how you can eliminate, because very often you don't get a physically sensible number. Or you can try to do absorption correction for your data process when you process your data. But again, you need to know very well geometry of your sample. You need to know the sample size, and usually we run this kind of samples, in double wall can. So we do know exactly, what is how much is can is field, and so the absorption correction, quantitative absorption correction of this kind of stuff is very difficult. It's almost impossible, I will say, and in this case, solution. So if you cannot get any sensible, physically sensible moment size, then yes, just fix it to 7 maybe, and refine absorption.
Okay.
Yes. Okay. Yeah, maybe Ruan can advise some better.
There is another problem in time of flight, is the dependency with wavelength, and the fact that what you have is a pseudo wavelength, because you have time focusing, and you have, for example, for a particular wavelength that you have a very high d spacing. In fact, you have neutrons that have a shorter wavelength, and then there is the formulas we use for absorption correction correct too much, and sometimes you are not able to refine very low Q peaks due to this absorption correction, which is not true that all the program use the same, but this is not correct. In fact, this is a problem with time of flight when you are
Yes,
using time of flight. You have a focus in time, and then you have, in fact, different wavelengths that enter. And then when you normalize the data, for me, it's impossible to correct that. That is not. You can put more complex absorption correction, but it's just something for fitting a little bit better. This is something which is a problem, really.
Yes, yes.
I don't know if you have seen the paper by Bob von Drill recently, just converting the time of flight to constant wavelength. Just using, like for example, in wind plotter, if you put Q,
yes,
then
yes.
you have something, and then you say, I have one single wavelength, and then you convert to 2 theta.
But it's a fraction.
But one of the problems related to this kind of things, why he has published that, is this kind of thing. Is that in fact the absorption correction is not good. It's something that is not
yes,
really physical.
But unfortunately, it is. Yes, it is a problem. And as I said, the only practical advice is just fix the moment size to physical value.
Yeah.
You know, forget. I mean, it simply means that your data cannot deliver you information about the moment size. Fix it to 7 maybe, and do the refinement, the rest of the refinement.
I mean, for me, this thermal factor, even at room temperature, they are quite big, no?
I don't know. This is not my data. I don't know much about this. I think there is some oxygen disorder here. It's probably static. Yeah, they're a bit big. I agree. Or another reason, maybe they're anisotropic, you know, and we are trying to, because this is a layered structure, and we are trying to reproduce them with isotropic. So if you, in final refinement, you need to pay attention on this kind of things, by the way, on the thermal parameter. And if it's big like that, you can try to refine anisotropically. That FullProf allows you to do that. Yeah, or maybe it's a problem with oxygen stoichiometry. So it's simply occupancy are not. So we have just less oxygen at this position, and it's trying to compensate that with the thermal parameter. But that depends on, again, you need to know your sample well as well. How susceptible is to oxygen non-stoichiometry and so on. Yes. It's here. So, for instance, Maria was talking, I guess, about this one. For instance, this is quite big, and this one is quite big. So I think it's probably simply because. So you can instead what you can do, you can put it at a smaller number, let's say 1, and try to refine your occupancy, and see. Usually they correlate, and if your actual oxygen content is less than that what in the model, then yes, your thermal parameter will be big. So I guess most likely that is the reason in the present case.
Okay, maybe there's many questions, but stop. And then probably we will go on to the tea break. And after that, we have a question time. So let's thank Dmitry again. Thank you very much.
Thank you.
So we will start in the 4:50.
Let's say...
Okay, 4:50. So 10 minutes? Roughly 10 minutes. Okay.